Okay, so I'm in charge of the AM section of the lab, and Professor Clifford is in charge of the PM section of the lab. We will be splitting the grading, so like I'll grade lab 1, he'll grade lab 2, so that way there's no like differences between the AM and PM section in terms of grade. Okay, so all of one lab will be graded by the same person, and then we'll be talking with each other if there's any discrepancies. Okay, so course overview. We meet on Tuesdays at 12:10 p.m., which is right now. And if you, I realize this is during lunchtime, so if you want to have snacks, that's cool with me, as long as it's not distracting. So avoid bags of chips. Our labs are tomorrow at 10 a.m. if you're in the morning section, and 2:30 p.m. if you are in the afternoon section. And we have a syllabus that's located on the Canvas page. There is a quiz regarding that, just to make sure that you've read it and you understand it. That's due on the 29th by midnight, and you do get a grade for that. So this is basically like gimme points, so please take that quiz. I have had people who have forgotten to take a core syllabus quiz, and it was a difference between them getting one grade versus the other grade. So please take it. We are organized into weekly modules. So each module has learning objectives that will tell you basically what information you need to know from that material that you're being taught that week. There's also pre-class assignments, such as like watching a demonstration video. Sometimes those are filmed by yours truly, and sometimes they are cheesy, for which I apologize. My cinematography skills have something to be desired sometimes. Also presentation material. So the lecture slides are available on Canvas. There's like a little notes format where you can like take notes on the side. And there's also, if you download the other version, the notes that I like, my little lecture presenter notes are embedded in there in that PDF file for you to open up to get like additional information and stuff like that. Some students find that very helpful. The laboratory materials are also available. So please read the lab before coming to class. Do watch any demonstration videos you're supposed to watch before coming to lab, so that way you're ready to do the assignment and have enough time to do the assignment. And then there are additional resources on each page, and those are just kind of to factor in the fact that people have different learning styles. Some people like doing like games, some people like watching extra YouTube videos. That's all just based on your learning style. They're not required, just whatever makes you happy to study better. All right. And then we do have the fundamental of laboratory mathematics, as well as the phlebotomy textbook that we'll use later on in the semester when we start talking about phlebotomy. All right, so at the completion of the course, so these are the course learning goals. You'll be able to identify common safety hazards, demonstrate proper technique, identify and describe appropriate use of PPE, describe the appropriate response to a chemical or biological exposure, operate basic laboratory equipment. You see how I have these verbs underlined as we learned in our orientation. These verbs tell you to what extent you need to know something. All right, that's why learning objectives are fantastic. And then apply theoretical knowledge and technical proficiency, apply the metric system of measurements, and demonstrate laboratory practice standards in safety, professional behavior, and ethical conduct. And then we'll recognize ethical issues embedded in the laboratory practitioner roles. So this is, there are more learning objectives for each individual module. This is kind of just the overall, our goals of the course. So some grading criteria. This is how kind of the grades break down. It's weighted. It's not just by point system, because I don't like being pigeonholed into this assignment must be 10 points. I like to have more leeway in my life than that, so that's why I use percentages. There is a laboratory competency assessment on September 14th, where basically you will show that you have learned how to use a pipette and a micropipette and use a spectrophotometer, and then a competency assessment on phlebotomy, where you basically go, I can stick this fake arm with a needle and get what fake blood to come out of it. So there's rubrics for those, as well as demonstration videos. And then there's the effective domain assessment that has to do with like your professionalism, coming to lab prepared. That means wearing the appropriate clothing for lab, showing up on time, attending lecture, things like that. Usually everyone gets all the points for that. And then we also have a written exam as well as a practical exam. All right. And you've already done your safety modules. I've already got everyone checked off on that. And we do have a lab math quiz tomorrow in lab in those first 35 minutes of labs. All right. Okay. So then, oh, also I'm nicer than the university, and I have my grade cut off slightly lower for each grade than the university standard. Yes, sir. Do you have a question?
For that lab quiz, math quiz tomorrow, what sort of stuff is we have to do with formulas?
You're going to have a periodic table and a calculator. I will have a periodic table for you because I want you to have the exact numbers on the periodic table that I gave you because that makes grading easier for me. Okay. And you'll be able to use your scientific calculators that you have in the lab. All right. So no unit conversions, normality, molarity, percent volumes, and hydrates. I think that's the bulk of it. It's not very long. It's like 1 page front and back. Plus, the space to like write everything out. All right. So the effective domain assessment, I already talked about this. Basically, it's are you acting professionally, cleaning up after yourself, coming to lab prepared, showing up on time, things like that, being ethical. And if you're not meeting expectations, then we will reach out to you and be like, hey, can you work on this? This is what we're observing. This is what we'd like to see. All right, so due to the hands-on nature of the laboratory courses, attendance is very important. It's very hard for us to make up these labs because the lab is pretty much busy the vast majority of the week, and the open lab period is only an hour long, and our labs are 2 hours long. So it's very hard for us to make up a lab. So unless you have an extenuating circumstance or an excused absence for a university-approved reason, we will not be able to do makeup labs. It's just really not feasible on our schedule. But we will try to work with you as much as possible if you're sick or you have university business. If you do need extra help or resources to master new material, please reach out to us. We want you to be successful, and the earlier you reach out for help, the more time we have to help you. All right, so don't come to me like the last week and go, I don't know any of this. And I'm like, well, we could have been working on that. So please reach out to us earlier if possible. All right, so now we're going to move into the actual content. So we're going to talk about pipettes and micropipettes. So pipettes, these are basically glass or plastic tubes. I was actually explaining to my daughter that I was going to teach this today, and she's like, what are those? I'm like, it's basically a fancy straw that you don't use your mouth on. Where they're open on both ends and they're used to transfer a specific amount of volume between containers. So these are typically used for volumes between 1 milliliter to 100 milliliters. Anything bigger than that, it just becomes unwieldy. Anything smaller than that, you're better off using a micropipette. And there are a variety of types. You might be familiar with some of them. A volumetric pipette, it delivers one volume. It does that one volume extremely well, but it only delivers that one specific volume. Graduated pipettes, they're capable of delivering a variety of volumes based on your need. And there's 2 main types of them. There are some other types, but they're weird and they're not commonly used. So we're not going to worry about them. There's the Moore and the serological. Most of the time, you're going to see a serological pipette in the clinical lab because the Moore pipettes are kind of stupid, and I will show you why in a minute. All right, so volumetric pipettes, these are used for accurate measurements. So they deliver only one volume, and they are calibrated to deliver that volume very specifically, very well. And so they're used when accuracy and reproducibility are crucial. So like I would use them when I'm making mass spectrometry standards. So they have this Class A designation that basically means they are very accurate. And as accurate, if you fill it up, that meniscus to the bottom of meniscus to the etch line, they are like really good at being accurate. So to fill it, you would aspirate the liquid. Some videos will show you rinsing it first, letting it drain, and then refilling it. And then fill it and let it drain so the meniscus is at the bottom of that etched line. And then you allow the liquid to drain out with the tip against the sidewall. And we want the tip against the sidewall because it lets that last little drop come out. Otherwise, it like has a tendency to cling to the outside edge of the pipette, and then you're not getting that last little drop. And you do not blow these out. These are designed to drain by gravity and to have it deliver that volume accurately solely by draining. So these are, quote, to deliver pipettes. Whereas the Moore pipette, these deliver a variable volume. They look a lot like a graduated cylinder, but they are not graduated to the tip. So if you look really closely at this guy, you see that the number here ends at a 5, and then there's no markings further down. You basically fill this up, fill it to whatever volume you want, and then you let it drain until it gets to that little line, and then you leave the rest of it in. That is annoying, because you have to then accurately stop it right then, and it's just really annoying to do. So we don't use these very often, but they do exist. So, and that last number is the capacity of the pipette. So if you filled it up to the 0 at the top and then let it drain, you would stop it right at that line and discard the rest. I really don't know why these exist. I don't like them. I've never actually used one in practice, but they do exist in the world. The serologic pipette, on the other hand, is my friend. So the serologic pipette does have graduations all the way down past this line. And that last ml is actually contained in the tip of the pipette. All right. So this also delivers a variable volume. So this is a good representation of seeing those graduations going beyond that final line, final large line. And these are more commonly used because you can let them drain completely. And then depending on the manufacturer of the pipette, they are either to deliver, meaning you just let it drain, you don't blow it out, or they are to contain, meaning that you would blow it out at the end. It just depends on the manufacturer. It's written on the pipette what kind it is. So pipettes have different specifications. So on the top part of each pipette, you will see like the brand name of the manufacturer. So like we have Pfeiffer and Kymax for these two. It will have the max capacity of that pipette, which is for this one is 10 mLs, for this one it's 5 mLs. And then it will also tell you what increments those gradations are at. So this one is in tenths of a milliliter, so it's every 100 microliters basically. And then it will say at what temperature it was calibrated at. Usually that's going to be 20 degrees because that's considered like standard temperature. It's room temperature essentially. And then it will say whether it's TD, meaning to deliver, or TC, meaning to contain. So sometimes they also have these double rings at the top. If there's a double ring present, that means it is to contain, and you would blow out that last drop. Most serological pipettes are going to have that double ring and be blown out. And that's because the pipette guns, if you've ever seen those, they're really cool. They're electronic. They're way easier to use than the bulbs. They don't let it drain by gravity. You actually have to press the button and it blows the liquid out. So it's just way easier to use a serological pipette that's designed to be blown out, because most of the time you're going to be using these fun guns. They're super fun. And then if it has a TD, that means it's to deliver, and you would let it drain out by gravity and you would not blow it out at the end. So when you're using the little simple bulbs like we have in our lab, it's actually easier to do a to deliver. But when you're using the pipette guns, it's easier to do a to contain pipette. So that's why there's different kinds based on what kind of lab you're in and which one would be most efficient for your workflow. All right, so there's different methods to get liquid into the pipette. Our mouth is not one of them. So I worked at my last job with someone who was old enough to have mouth pipetted, and she would still be known to sometimes do that if no one was around, which is gross. Anyway, so there's different types of bulbs. There's these cool little rolly kinds. You basically like roll it up and down. These are really nice because you're not trying to like catch the liquid before it falls. So if you're not getting to use a fancy pipette gun like this kind, then these are pretty good. And you also have like a little quick release button so it drains by gravity. And there's ones that will do a set volume. We have these blue ones. Sometimes they're red in our lab. You will get to experience the joys of those in 2 weeks in our lab and understand the frustration of them and begin to appreciate why pipette guns are awesome. And then there's these cool red ones where you, like, depending on where you click it and stuff, let's say like release or empty and stuff. There's videos on how these different bulbs work at this link down here at the bottom if you want to see that. I think this link is also available in the additional resources on module 2. So sometimes our pipettes need to be sterilized, and we sterilize them through a process called autoclaving. We actually have an autoclave in our prep room. It basically applies high heat and pressure to the material, and that kills anything that's on them. And we autoclave them in these special canisters. They can be metal or plastic. And then we basically assume that our hands are raining down germs at any given point. So whenever we go to grab them, we gently shake it on its side, and then we basically touch only the one we need to grab it out, and then we immediately close it so that germs cannot like get in there. So if you ever do cell culture, you'll get extremely skilled at this. And I think you get to practice this skill in microbiology as well. So then we have our micropipettes. So these are designed to transfer volumes between 0.5 microliter, which is super, super tiny, and 5 milliliters, or 5,000 microliters. And these can be fixed volume, where they do one volume very accurately, or you can have variable volume. These are the most common because then you can use them for, you know, whatever thing you need to use them for. And they either work by air displacement, which is the kind that we have in our lab, where it basically acts kind of like the bulb, where it just sucks up air and the liquid follows. Or it can also work by positive displacement, and that's more similar to how a syringe works, where you have that like plunger that you pull out and the liquid follows it. So there's actually a piston in there that will draw up the liquid, and these are very helpful if you have a very viscous sample. So sometimes there are body fluids that we receive in the lab that are not liquidy anymore. We'll say they're very gelatinous, and that's when you need a positive displacement pipette in order to accurately pipette those. All right, so reading the readout on the micropipette, so what volume do you have it set on? So there are different sizes of pipettes, and they each have a range of volume that they are capable of delivering. So they're typically called P and then fill whatever number their top volume is. So there's a P20 that will go between 2 and 20 microliters, a P200 and a P1000. Those, generally a lab is going to have those three because the ranges of those overlap in such a way that you can go 2 to 1000 without any gaps. So when you're reading these readouts, depending on the manufacturer, they're going to have a red number on the P20, and that indicates that red number is after the decimal place. So for this one in particular, this is 2 microliters, whereas this one is 20 microliters. For the P200, we're not going to really be using decimal places on a P200. It's not that accurate. So you're not going to have any red numbers. It's just going to be what you see is what you get. And then for the P1000, they did something to show that it has the thousands place. In that case, usually that number is red, and that indicates the thousands place. So for this one, that one right here is actually 200 microliters, but they're not showing that last zero, which can be confusing. But a P1000 does not go down to 20 microliters. It only goes down to 100. That's kind of how you generally know the range of each one. You know, well, I know it's not 20, it doesn't go down that low. And then it has the 1000 to indicate this is the thousands place. And then we have the parts of the pipette. We have the push button at the top, the ejector button to eject the tip so you don't have to touch it because usually it's covered in something gross. Depending on the model of the pipette, you can have a black dial like this that will allow you to adjust the volume. Some of these have little locking rings that you can move up into place so the volume doesn't change if you're continually using it. And then there's the shaft, and that's kind of where the air displacement happens. There's an internal piston that helps draw up the air, and then you attach a disposable tip onto the end of the pipette, and that is where the liquid is actually drawn into. You should never actually be getting liquid into your pipette. That is bad. Don't do that. We'll play with those tomorrow. All right, so a P10, that's a smaller size. This is usually used for like molecular diagnostics, right? Yeah, we got those. They're fun. So these go 1 to 10. Then we have a P20 that goes 2 to 20, a P100, which is what most of you are going to have in the lab. Some of you might have a P200, depending on, we don't have enough P100s that go 10 to 100, and the P200 goes 20 to 200, and the P1000 goes 100 to 1000. You see that there is overlap in these. So if you buy a P20, a P200, and a P1000, you've got the full range from 2 to 1000, which is really nice. So you don't have to buy 5 pipettes. You only have to buy 3. So you want to choose, when you're selecting which pipette to use for your procedure, you always want to choose the pipette where that volume that you are delivering is at the upper end of that pipette. So if you need to deliver 100 microliters, you could use the P1000 because it's technically in range, but you'd be better off choosing a P100 or a P200 because these pipettes are more accurate at the upper end of their range. And I'll show you a table on the next slide that highlights that. And you also want to avoid double pipetting or even triple pipetting because you might be like, okay, I need to deliver 2 mLs. I'll just use my P1000 2 times. That's fine. It's not fine. It adds double the inaccuracy and double the imprecision when you do that. So if you have to go above the range of your pipette, go get a volumetric or a serological pipette. I know it's annoying to use the bulbs, but it's going to give you a more accurate result. So I know it's tempting. I've been guilty of it myself, but don't do it. All right, so micropipette manufacturers publish these acceptable limits on the accuracy and precision of the pipettes. And there are ways that you can check these using an analytical balance. You'll do that exercise in the clinical chemistry lab next semester. But you have to make sure that these micropipettes are calibrated periodically. Usually it's every 6 months to every year. depending on the lab's protocols that they need to be checked to make sure that they are still accurate and they're still precise. So one thing I'm going to highlight here, if we look at our P20 at 20 microliters, its accuracy is within 0.16 microliters at the top end of its range. So if you're trying to pipette 20 microliters of the P20, you're going to be pretty close to 20 microliters. Whereas if you grab your 200 and go down to its lowest volume it can do, which is 20, you're going to be 1.6 plus or minus from 20. That's not nearly as accurate. And same with precision. The precision is more than double. The imprecision is more than double doing the P200 pipette at its lowest volume than using the P20 at its highest volume. So always choose the pipette where you're at the higher end of that pipette. It will give you the most accurate results. And we like accuracy in the lab. And then highlighting again, so the P100 at 100, you have 0.8 versus the P1000 at 100 is 8 microliter difference. You could have up to an 8 microliter difference, and that still could be considered acceptable for that pipette. So always use the upper end of the pipette, if possible. All right, so we can check the accuracy of our pipette by basically pipetting a set volume of water onto an analytical balance and calculating, okay, I set it to 20. I have now theoretically pipetted 20 onto the analytical balance. I have recorded that weight. I know that 1 milliliter of water equals 1 gram of water under ideal conditions. It does vary a little bit based on temperature, but we're not going to worry too much about that. And I'm going to see, did I actually pipette the 20 microliters that I thought I pipetted? So you would take your expected volume, which is 20 microliters minus whatever you actually pipetted, say 19.2, and that would be your mean difference. And you do that multiple times, usually about 5 to 10 replicates. And then you can calculate your percent error, where you take your mean difference over the expected volume and multiply that by 100. And that's where these numbers come from, the percent error and the mean differences from those equations. Whereas precision can be checked by your pipetting and weighing the same volume repeatedly on your analytical balance, recording all those values, and then calculating the standard deviation and the percent coefficient of variation. I am not going to ask you to calculate standard deviation by hand. No one needs to do that in this class. You can use Excel, all right? But I might ask you to calculate it from variance. So if I gave you the variance of something, you would need to know that standard deviation is the square root of the variance, all right? And then you'll need to know how to calculate the coefficient of variation, which is the standard deviation over the mean volume times 100%. And what's nice about the coefficient of variation is that it basically calculates, it normalizes for the size of things. So if you're looking at 2 microliters versus 20 microliters, it basically helps erase the fact that those are 2 completely different numbers and lets you compare apples to apples instead of apples to oranges. So that's why the coefficient of variation is very nice. There are also these cool kits that manufacturers made. It's a dye kit, and you can check the micropipette calibration spectrophotometrically using a spectrophotometer. And so there are these standards here that have a set absorbance and amount of dye in them, and then you make a standard curve or measure the absorbance of each of these and plot them on a graph. And then you would take these little tubes, these just have clear liquid in them, and you say, okay, I want to check my pipette at 20 microliters. I'm going to open this clear tube. I'm going to take 20 microliters out, discard that, and then I'm going to add 20 microliters of this red dye in there, mix it up, measure the absorbance, plot it on this curve, and see what volume I actually pipetted. The problem with these are every time you have to use a new tube for each volume you're checking for each pipette, so it can get very cost prohibitive very quickly, especially if you're calibrating a pipette and you're kind of having to like guess and check as you change the calibration. It just gets very cost prohibitive. These kits are not cheap, whereas an analytical balance, once you have bought the analytical balance, that's free to use, right? You have to do a little maintenance, but it doesn't cost you money every time you use it. So that's why the weighing version is preferred. But for smaller labs where they don't have a lot of pipettes, this works. It exists in the world. All right, I'm sorry guys, but I do have to talk about safety again. I know you're a little safetied out. Yes. No, just the stuff that was in the summer pre-work. So just the unit conversions, just the hydrates, all that stuff that was in that basic concept handout. None of this. All right, there are practice quizzes online, by the way. New this year, FYI. All right, so we're talking about lab safety. I know y'all are tired of it. Okay, so the goal of lab safety is to prevent accidents from happening before they happen. So over the last few years, there's been some high profile cases where people have died or been seriously injured in lab accidents. So this woman, she didn't tie her hair back. She was working in the lab and her hair got caught in a lathe and she got asphyxiated by strangulation. This woman was working with a chemical that is very reactive to exposure to air. A syringe plunger popped out of the back of her syringe and it exploded, and she hadn't received proper safety training on how to use that chemical or where the appropriate safety showers and stuff were. So she died from the burns that resulted from that incident. And this one, no one died in this one. There was a flammable safety cabinet that didn't have properly fitted shelves in it. So when they were loading up some chemicals into there, the shelves collapsed, bottles broke, chemicals mixed, everyone had to evacuate because of fumes, and it combusted. So they completely ruined that lab, and I'm sure the boss was not happy about that. But no one died, so yay. But all these could have been prevented with proper safety. So why do these types of accidents happen? And that's usually due to insufficient training, insufficient hazard evaluation and mitigation, not wearing the appropriate PPE, or failure to follow safety policies. So even with training and careful attention to protocols, accidents can still happen in the laboratory. So everyone is responsible for their safety. So you have you responsible at making sure that you're doing what you've been trained to do, and us as the faculty to make sure that you have been properly trained so that we can avoid accidents. And we also have environmental health and safety that adds support and makes sure that we're following the rules. And our department has a compliance officer to make sure everything's going the way it should. So reporting incidents, you want to report incidents, near misses, unsafe conditions, and don't feel like you're going to get in trouble if you report something. Like if you see a piece of equipment that has a sketchy power cord, please let us know. We're not looking at the equipment as much as you are. So please let us know if something looks off, or you're like, is this the safest way to do something? And we'd be like, oh, maybe not. I hadn't thought about that. So please let us know. Because we want to avoid serious injuries, and the best way to do that is to catch them before they happen. All right, so hazard identification and risk management. So these are in bold because you do kind of need to know these definitions. So a hazard can cause harm or adverse effects, and a risk is the chance or probability that a person will be harmed or experience an adverse effect if exposed to a hazard. And then the risk assessment is the process where you basically identify the hazards, analyze or evaluate the risks associated with that hazard, and determine the appropriate way to eliminate or control the hazard. So basically act like you're very paranoid and see danger everywhere, and then figure out how you're going to fix that danger. And then you perform these hazard identifications and risk assessments prior to introducing new procedures or new chemicals or new equipment, and basically be like, what could possibly go wrong? This is when it's your moment to be paranoid, where being paranoid is a good thing. All right, so hazard identification. So health and physical hazards to chemicals and equipment being used. You want to identify those hazards. So you can do that by reading the labels, reading the safety data sheets, which are available online for all of the chemicals we use in our labs. So there's health hazards, basically indicates that it is harmful to your health. So something that's like a carcinogen or a corrosive or a developmental toxin. So if someone's pregnant, they usually reach out to us when we go through our labs for the semester, and we go, okay, well, this lab has a reagent that's could be potentially harmful. Can we substitute it out for this student with something else? And then there's different routes of exposure, inhalation, contact, ingestion, things like that. And then there's physical hazards. So like you can be working with a chemical that reacts to air. You can be working with a chemical that really doesn't like getting warm. I've worked with chemicals that you had to store them in a flammable freezer. And then whenever you were using them, they had to be worked with in liquid nitrogen, because if they got too warm, they would explode. So there's also some reagents that if they're not stored underwater, they explode. So being aware of what those chemicals are and how you're supposed to handle them helps prevent accidents. And you always want to receive new training for any new procedures and using any new equipment, and then report your concerns to your supervisor, which would be us, the faculty. All right, so there are certain ways that chemicals have to be labeled. So the chemical has to contain the chemical name and its CAS number, and then the supplier has information on there like who supplied it, who's the manufacturer of it, and then there's signal words like warning, danger. They're usually fun colors like yellow, red, orange, so that you see them. And then there's hazard statements that basically say like, this is a carcinogen, you know. And then there's these new hazard symbols and pictograms. These are the HAZCOM standard pictograms. You'll see these a lot on our reagents, because unlike the numerical system, where I myself am always like, I know 4 is a bad number, but I don't really know what that means. So that's why these HAZCOM pictures are used, because it's like, that looks like something exploding. I got that one. I understand exploding pictures. Whereas these numerical systems, they tell you based on what color it is, how dangerous it is in each of these categories of health, flammable, reactivity. But it just gives you like a scale. It doesn't tell you actually what like the problem is. Like if it's reactive, is it going, and we died. Is it going to react with, I've lost my words. Is it going to react with water? Is it going to react, like what's it going to react with? So these numbers aren't the most helpful. You're not seeing why I have backup batteries. No, I believe in me. Back to this. All right, so this is kind of an example of what a chemical label can look like. You can see this nice orange box that has that HAZCOM picture in it saying that it's toxic. There's also a statement on the back kind of detailing in more detail what exactly is the problem with this or the danger of this chemical. You'll see the name of it, the CAS number. Sometimes they'll put lot numbers on there. So we have our hazard statement. There we go. Our hazard pictogram. And then this is another example by a different manufacturer. You can still see this numerical. They have both the numerical rating system as well as the pictures. So they kill 2 birds with 1 stone. Am I back? I'm back. Okay. So there's different ways that different manufacturers label these. So it's a good idea to just, you know, look at your label when it comes in and be like, what am I messing with today? All right. So a lot of times we're not getting something from the big container, right? Because we don't want to contaminate the big container, or we've diluted it in some way, or we're making a reagent. So we have a secondary container. And as we learned in the lab safety training, the only time you are allowed to not label a secondary container is if you are working with it right then and you are not walking away from it. All right. If you ever need to walk away from it, you must label it. I think it's always a good idea to label it just in general, because I like to have the general premise. What if I drop dead right now? Because that is essentially what happens during a shift change. You leave, someone else takes over for you. So secondary containers have to have the name of the chemical. You don't need to put the CAS number on there, but you have to have the name of the chemical, and you have to have the appropriate hazard warnings on there. So a lot of times labs will have little rolls of stickers with the appropriate HAZCOM pictures on there. Like here, they just put on the 2 little stickers they needed, and then it's labeled, and you'd have fun putting stickers on things. Who doesn't love putting stickers on things? All right, so safety data sheets, they contain the manufacturer information, the chemical names, any synonyms, the CAS number, any ingredients if it's like a complex, not pure thing, exposure limits, detailed hazard information, any symptoms of overexposure, as well as first aid that needs to happen, and then the chemical and physical properties, and then precautions for safe handling, use, and disposal of that. And these should be available for every chemical in a lab, whether online or a physical copy. You can access yours on your iPads, or we can help you access them should you need them. All right, so there are different types of risk assessment tools called safety controls, and we need to identify different controls. So administrative controls, and you will need to know like how to classify each of these, like what's an administrative control, what's an engineering control, what's PPE. So you'll need to be able to classify these. But an administrative control is basically anything that you think of like signs, training, anything that you think an administrator would handle, like something you could do on a computer is my general like thought process for it. So making sure you have prior approval to do something, whereas engineering controls are more like physical things. So things like having a fume hood, having a gas cabinet, locking the gas cylinders into place, putting things in the appropriate storage cabinet, separating acids and bases, putting something in isolation. All of these like physical sort of things that you can do to prevent health hazards. And then personal protective equipment is basically anything you're putting on yourself. So this is your lab coat, your gloves, your safety glasses, your face shields. Sometimes you need an N95 respirator if you're working with like tuberculosis or something. Making sure you're wearing closed-toed shoes, your hair is tied back. All of those are PPE or personal protective equipment. So some examples of engineering controls. So these are some types of fume hoods. We have some with tops with sashes that go up and down. And there's a little arrow at each sash where it needs to be below that arrow for it to work properly. And usually they will alarm at you if you go above that level. And then there's also side sashes where it will open up, where you kind of push both doors into the middle and you kind of work around it like this. You want to elevate any large objects. You want to be working within you want to work 6 inches into the hood so that you can ventilate appropriately. You don't want to use it for excessive storage. I have been into some research labs where it is literally just chock full of stuff that are just storing in there, and that is bad practice. You want to avoid rapid movement so that you're not making huge currents of air and causing things to like come out at you. There are alarms on there, and they do get inspected at least annually and checked to make sure that they're working. And if they aren't working, they yell at you and then you can't use them in blood section. All right, so there's also other fun laboratory ventilation. So sometimes you just have kind of like, your fume hood over your stove. They have these over instruments that make a lot of fumes. Like this is a liquid chromatographer, it looks like. And they also have some other kinds. I think these are cool, where you actually like put your hands into these cool rubber gloves and like work in there. Those are nifty. I have never gotten to use one of those. I feel like I've missed out in science. And then there's also things like storage cabinets. So we have flammable liquids are stored in a storage cabinet. They also make flammable refrigerators and freezers. You also have corrosive storage cabinets. You want to make sure that things are appropriately segregated. So do not put aqueous things next to water reactive things. Don't put acids next to bases. Don't put pyrophorics next to a heat source. Like keep dangerous things away from something that will make it more dangerous. And then compressed gas cylinders. If anyone's seen Jaws, you know the potential of these. So they are that compressed air. Basically, if anything happens to that cylinder, it becomes torpedo and it becomes very dangerous. So we do a lot to make sure that these don't fall or they don't get punctured. So they're always like chained up to something. You have special carts to move them around the lab. They should always be like contained. And you have to use the appropriate regulator and tubing for the type of gas you're using. Don't substitute out if you're not sure that's compatible. You want to make sure that you're ventilated, and you have to make sure that incompatible gases are segregated. I once worked with nuclear magnetic resonance machines, and they have a tendency to quote quench, where basically all the nitrogen gas will just flood out of it for no apparent reason. You basically just have to run if that happens because it sucks out all the oxygen in the room. So sometimes. So then for personal protective equipment, we wear our knee-length button-up lab coat. Why would we want it to be knee-length? To cover our lap when we're sitting. I don't want to stand all day. It's got to be buttoned up because otherwise it can still get on your clothes when it's not buttoned up. You got to wear a face shield if you're moving something that could splash at you. Sometimes they have like these little manual shields. It's like basically a plastic thing that you're working behind around it. But a lot of times it's just easier to wear it on your head. Safety glasses that are impact resistant, long pants without rips or holes, full coverage shoes, like sneakers, though we don't like it if they're mesh or anything that's going to quickly wick material. So the back of the heel has to be covered because sometimes there's a lot of mechanical equipment in the lab, and there have been instances in the lab where people have like been standing next to equipment and the back of their heel has caught on something like the underside of a refrigerator and they like cut their heel. So we want to make sure your entire foot's covered. Any long hair is tied back. That includes if anyone has a glorious beard, if it's super long. The general rule is if it goes past your shoulder, it needs to be tied back. You've got to wear gloves. Sometimes chemical resistant ones are needed if you're working with a particular type of chemical. And you may be required to wear a face mask or respirator. All right, so then we have our disposal of laboratory waste. Non-contaminated glass goes in the non-biohazard glass container like this. We do have these in the prep room. Should you need them, just let us know. We don't keep them out because usually most of what we're working with is contaminated. Biohazard, that's things like your gloves, your micropipette tips, plastic tubes. I think we're doing the micropipette tips go in the sharps container, right? If it pops the balloon, it goes in the sharps container. I personally think that glass should go in the sharps container because if it breaks, then it's punctury, but different universities have different rules. So we're going to go with the rules that we were taught during lab safety week. And then sharps go in the sharps container. So anything that will pop a balloon goes in the sharps container. And then we have liquids will go into our decant buckets, and then we take them and put them into secondary waste containers to be disposed of by EHS once they get filled up. And if you are uncertain of how to dispose something, please ask. Remember, gloves do never, ever, ever go in the regular trash, even if they are clean. It is the appearance of evil, all right? If it looks like it could be something that is normally biohazardous, assume it is biohazardous. All right, so then biosafety in the lab. So basically you have to have systems in place to help prevent the transmission of disease-causing infectious agents, because when you receive a sample from the hospital, you don't know what's wrong with that patient. You don't know if they have HIV. You don't know if they have hepatitis. You know nothing about them. You just know their name and their medical record number. That's literally it. So we always want to practice standard precautions, which is an infection control process designed to reduce the transmission of infectious agents between patients, hospital personnel, and laboratory personnel. So basically there's a system of barrier precautions where we try to avoid touching gross things. We're trying to avoid touching biohazardous materials. So we wear our PPE, we wear our gloves. So the only body fluid that we don't care about is sweat. Everything else we assume is gross. So blood, body fluids, secretions, excretions, tissues, non-intact skin, and mucous membranes, all of that is considered gross. And if ours mucous membranes and non-intact skin is present, then we have an avenue of something getting into us. So if you have a cut on your finger or something like that, please put a Band-Aid on. All right, so in case something happens with your glove and it pierces, you now don't have an open area on your hand that is liable to get something into it. And then universal precautions is the general idea that we treat everything as though it is contaminated, that it is potentially infectious. We do not make any assumptions about anyone. You don't think, oh, well, this is a baby sample. They haven't had time to get sick, you know? You don't know their mother's life, right? Some of these are passed from mother to baby. So always assume everything is potentially infectious and treat it as such. All right, so we talked about how to clean up a biohazard infectious specimen spill last week. Remember, wear your PPE, contain the spill with paper towels, making a little barrier, little dam around it, and then saturate it with bleach, assuming it is not a chemical. Remember, this is only biohazards that we use bleach on, using our little dam process around the outside perimeter and then soak the middle so it doesn't spread outwards. Wait 10 to 20 minutes, at least 10 minutes for the bleach to work. And then discard the contaminated material and the biohazardous waste. And if it's a very big spill, we do have very large spill kits for that. I have yet to have to open up one of those. I'm slightly excited to do it one day, but also scared. All right, then we have electrical safety. Extension cords and power strips. Extension cords should only be used for temporary setups. You shouldn't be relying on them to like power big, huge equipment all the time. You should secure cords to prevent tripping. Don't daisy chain them, meaning like connecting one power cord to another power cord to another power cord. That's okay for Christmas lights. It's not okay for the lab. You want to make sure that it's appropriately rated for the electrical load that you are going to be using it on. Fun fact, mass spectrometers, these are freakishly huge $1 million instruments. They use a ton of energy. You usually have to have like an electrician come in and like build an entirely new outlet for you. It's kind of like a dryer, needs its own outlet. And power strips have to have circuit breakers. Don't use equipment with damaged or cords or plugs, and never attach an exposed connector like an alligator clip to a power supply. This is an example right there of an alligator clip. You might have used those in like high school physics class or something. I like this one. It's like, what were they hoping to attain with this? Like, I don't know what they were hoping for. That's bad. I don't even, they had to get extra equipment to rip that off. Like what? I don't know. People do crazy things. All right, so then equipment safety. Don't remove or alter any machine guards. Don't take away safety features. They are there for a reason. Wear safety glasses with side shields. Remove any jewelry that can be caught in the machine. Tie your hair back. And on some equipment, you want to roll up your sleeve. That's why I like the little elastic cuff sleeves, because they're not really going to get caught on stuff. Also, I have a tendency to knock things over, like open bottles over with my sleeve when I'm not paying attention. Another fun safety trip, never assume you're not going to knock something over, and always cap it right away. You will get burned by this a few times, and then you'll remember that. Do not work on equipment until you have been trained to use that equipment. That is one reason why we have demonstration videos for some of our equipment, that is your training on how to do it, because we can't do one-on-one training with all of you for every single thing. So watch the demo videos and never work alone. You are not allowed to be in our laboratory alone. That is how accidents happen. There's always a buddy system. Technically, you're not allowed to be in our laboratories without a faculty member, because we are technically your supervisors and are making sure that you stay safe. All right, chemical safety. Wear the appropriate PPE, utilize the engineering controls, wear the appropriate, use your resistant gloves, fume hoods, splash goggles, store them safely, dispose of them safely. Chemical spills, they should all be cleaned up in a timely fashion. Don't default to bleach. If it's a really big spill, please call 911 and evacuate. And we can call EHS, and they are capable of cleaning it up for us. Close the fume hood if it's in a fume hood. And if it's a small spill, we can usually handle it ourselves. And notify people around you, any emergency response personnel, if any unusual hazards exist. Usually there's information outside of each lab saying this is generally how dangerous everything is in this lab. That's an administrative control. All right, so fire, there's different fire extinguishers for different types of fire. Pull the fire alarm, rescue yourself, try to contain it if it's small, try to extinguish it, but I would prefer if you default to running away. All right. And then if you get to use the fire extinguisher, you will pull the pin, you will aim it at the base of the fire, you will squeeze the handle and sweep it in side to side motions at the base of the fire. I've never gotten to use one of these. All right, so then emergencies, you want to use the eye washes, flush your eyes for 15 minutes. Your eyes do have to be open for this. They forgot to mention that in the training the other day. So it's not fun. 15 minutes is a really long time. They get checked periodically, don't block them. And then we have safety showers where you have to strip yourself and stand under that for 15 minutes. And hopefully it's a safety shower that has a drain underneath it. Otherwise it's a huge mess. And then emergencies, seek medical attention. First thing to do, especially if you have eye contact with the chemical, flush your eyes first, let someone know, be like, ah, crap, something's happened. And while you're flushing your eyes, someone's probably gonna come over and like help you hold your eyes open. And other people can be, you know, calling emergency people. If you have a significant chemical exposure, if you have any chemical exposure that results in symptoms, so like if you're coughing because you've inhaled something, sometimes I forget that glacial acetic acid is a big deal and I don't think I need to use a hood. And then I'm reminded of the fact that it is a big deal and I should use a hood. If you have any burning or severe irritation and any electric shock, if there is electric shock, please remove yourself. Like if someone's like actively being electrocuted, do not touch them. Find the electrical source and like turn it off, like turn off the power to the room. We have breakers in the lab. And laser injuries, y'all aren't really going to be using lasers in our teaching lab, so that's good. Don't shine lasers in your eyes. All right, that's it. That is the last of the safety for the somewhat foreseeable future. Thank you for going through that with me. All right, and we ended on time. Woohoo! All right, so remember tomorrow you have quiz. Your microscopy activity is due tonight at midnight. If you haven't submitted it, please make sure you submit it on 3600. If you did submit it on the Canvas on the undergraduate page, I will download it and like move it to where it needs to be, so don't worry about it. All right, and if you need to make edits and you're having a struggle, please download Adobe Acrobat. We do have, every student gets a free license to all of Adobe, which means you get Photoshop and Premiere and all fun stuff. But that's a great way to edit your PDFs.